always minimize?
Yeah, I'll move them off, Mark.
Well, I just minimized it on mine, so.
Oh, okay.
Okay, folks, here we go. There was a lot of questions when Andy gave his very good presentation on filters about cameras themselves. And so that sort of encouraged me to do this presentation on the topic of different types of cameras, because there's always enough new members that these questions come up, and sometimes the existing members have questions. So since I used to be involved in a business that used some exotic CCDs and other technology for the projects we used to build at my old company, I have a little more insight than most people into this. Plus, I'm an electronics guy. So, okay, so there's, first of all, just to backtrack to go where we came from, before there was all this electronics imaging, it was all photographics. And basically the way most of us did it in the hobby was with single lens reflexes with film. And that could be black and white film. It could be positive, or also known as print film, or it could be transparency film. There were also specialized astronomical emulsions, which had special spectral sensitivities. It's the equivalent to what we do now with filters. And some of those were on film and some of them were on glass plates. In fact, if you go way back in time, the gold standard for doing astronomical photography was glass plates, where they actually took a plate of glass, very high quality, and they put the chemicals on top of it. And this was pretty much the way most of the old 1950s through 1970s work was done at places like Palomar and other professional observatories.
And they had to cut them with glass cutters.
Well, yeah.
To fit the cameras, without breaking them, yeah.
Well, that's different, yeah. Some of the cameras actually had curved film planes, and they actually had to use special thin glass just to do that. But that's a side issue. Sometimes people in the film days used larger format film, 120 and 220 film. Some people filled their cameras with nitrogen gas to make it more sensitized. Some people baked their film to reduce the so-called reciprocity failure effect. And some people even cooled their cameras. Thankfully, most of this is overtaken by events in the digital age. But there's still a lot of variety in what's done in the digital age. And a lot of that depends on what you're trying to do, your goals, and it also depends on your skill level, and it also depends on your wallet. But there's two principal types of cameras that are used in astronomical photography. There are cameras used for planetary, solar, and lunar work. And those are typically characterized by high frame rates and by the fact that you have plenty of light coming from the subject matter. The moon, the sun, or the planets, they're very bright. Go look at Mars right now, for example. It's got a much higher surface brightness than any galaxy in the sky has, or any nebula. The other type of photography is the long exposure or deep sky photography, and that has a different set of requirements than the planetary, solar, and lunar. So they're different problems and they have different solutions. One of the first things you'll hear when you get in this racket is CCD or CMOS. CCD stands for charge coupled devices, and it's really an architecture of the sensor. CMOS is really kind of a misnomer also. It stands for complementary metal oxide semiconductors, but it's also an architecture. So it's kind of confusing. On the one hand, they're talking about a processing technology, material processing, not software. And in the other case, they're talking about a sensor architecture. So they're really kind of confusing terms to a lot of people. And they are confusing because they really fundamentally come down to differences. So you'll hear about CCD sensors and CMOS sensors. You'll also hear about color and monochrome. So what's going on here? Well, in the first place, all digital cameras use pixelated sensors. They have individual little dots that detect the light photons. The difference between the so-called CCD and the CMOS is the way in which they're read out. And I'll talk a little bit about that. Both of these, CCD and CMOS, come in both monochrome, which means they have no filter in front of them in the sensor. You can put a filter on outside that, but the sensor itself has no filter. Or you can get sensors in which every individual pixel has a little individual sensor color filter sitting on top of it. So this is this is the filter array, the sensor array. And if you zoomed in on it in the case of a color sensor, you would see all these individual little colored dots, and each of those is a pixel. In the case of an unfiltered sensor, all of these would look the same. So that's the difference between a color sensor and a monochrome sensor. In a color sensor, every pixel has a little color filter on it, 2 greens, 1 red and 1 blue, because the human eye sensitivity peaks in the green. So they're trying to match the human eyeball. Each of these together, either merged or interpolated between, becomes a color pixel. In the case of a monochrome sensor, each pixel sees the same thing. A charge coupled device is called a charge coupled device because it detects the charges that's coupled between 2 different electrical conductor plates. CMOS is totally different. Each detector is totally standalone. It has its own readout, its own amplifier. In the case of a charge coupled device, these things are rooted out in groups to be read out. All sensors, the active area, whether it's a CMOS sensor or a CCD sensor, all sensors have to have electronics that are connected to them to pull out the digital logic, to amplify the signal, to convert it from analog to digital, and a whole bunch of other stuff. So when they talk about the sensor, it's more than just the active area. It's all the support electronics. So when the people who make your cameras, whether it's a digital camera that you can shoot in your backyard with, of your garden, or it's a digital camera that's used for astronomy, the actual sensor chip has this active area and it has all this support electronics built into it.
Wow.
So, and the basic difference between a CCD and a CMOS is not so much the chemistry of the materials, but it's the way in which it's read out. And CCDs, there's at least 4 different ways they read the data out. The simplest one, they pull the data out of each of the pixels in turn, in sequence, and they shift them in and then convert them to a digital signal. In the case of a CMOS readout, every pixel has its own conversion circuitry and it's read out that way. The fact that CCDs often read out by the column is why sometimes if a column fails in a CCD, you'll see a black line because this entire column is gone. There's ways to interpolate to get rid of that effect in software afterwards. But there's at least 4 different ways to read out CCDs. CMOS, they all read out the same. It's much simpler.
Mark, is that a cold pixel you described?
What?
Was that one where you said that, it's all black? Is that what they describe as a cold pixel?
No, I was talking about an entire line is missing, not
Okay.
an individual pixel. If one of these shift register bits fails, so that when this data comes shifted
okay.
down, then this entire column fails.
Okay.
Whereas with the CMOS, each one is individually read out. Now that requires faster processors. So in the early days, this had a huge advantage because it could be done with much slower support electronics. This requires faster processing and analog processing to pull out the data fast. But of course, as we all know, processors have gone from a few tens of megahertz up to gigahertz now. So that, along with other things, are causing CMOS to become much more popular. I mean, to put it in perspective, all of your digital cameras that you go around and shoot pictures, or all the dancing cat videos you see on YouTube or TV, those are all taken with CMOS because they're much cheaper to make in bulk. CCDs are more expensive, and as a result, the cameras are more expensive. They do have some advantages, but that shifts with time. As technology changes, as people improve things, the battle between CCD and CMOS has gone on for decades now. Right now, CMOS appears to be winning because of economics and because the processing technology has gotten better. Okay, so this is what the sensor looks like when it's sitting in your camera without the support electronics. That's often on the back now. It's in a little frame. This is the active area. There's a little frame. And they have to put some kind of filter in your regular digital cameras. They glue a little filter to these edges. And the purpose of that filter is that these detectors, whether they're CCD or CMOS pixels, they're very sensitive to infrared. And as most of you know, camera lenses cannot work in the visual and infrared simultaneously. It's impossible for the designers to do it right now. Now, maybe if they make new types of optical glasses, they can do it. Right, right now, if you go buy an APO refractor, it pulls the visual spectrum all the way from blue to the red and puts it at the same focal point. If you buy an achromat, there's a difference. But even the most expensive APO cannot bring infrared, visual, and UV all to the same focus. So the way they get around that is they put a cutoff filter on top of the sensor in normal digital cameras. By that I mean consumer digital cameras. So they put this IR blocking filter on top of the sensor so that the camera lenses will work. Well, some of the earlier cutoff filters actually ditched the hydrogen alpha, which is of course what you're looking at with most nebulosities, like the shot Jim Reynolds showed. So if you have that normal cutoff filter there that eliminates the IR, it also eliminates the hydrogen alpha. So the solution for a long time was you'd go give somebody $400 and they would dismantle your perfectly good camera and pull that filter off. Or you would buy a camera without a filter from Canon and pay $400 more for them to take off the filter, for them to build a camera with no filter. But they would charge you $400 more because it's viewed as a premium item. Anyways, interestingly enough, the newest models from Canon, Nikon, and Pentax actually have much better IR cutoff filters. So the need for that seems to be going away. When you buy an astronomical camera, whether it's CCD or CMOS, they don't have this problem. So if you buy an astronomy specific deep sky camera, it won't have that silly filter on it. Okay, this is just a generic picture to show you, no matter what type you have the pixel array, you have to index which column you want to read off, the row drivers pull the signal off, it goes through an A to converter, and voila, it goes to your memory card. So the designers have to worry about all this stuff. You and I don't, except that sometimes this circuitry actually generates noise, and sometimes it generates heat. And that's why we have cooled cameras in astronomy, to take that heat out, among other things. Okay, so that's sort of an overview of astronomy cameras. So there's, as I said at the beginning, there's two types of astronomy cameras. There's lunar, solar, and planetary cameras, and there are cameras used for deep sky objects that have different sensitivity characteristics. So this is where we get into the nuts and bolts. So what's going on with the solar system camera? Well, you're after the maximum amount of detail on medium to small objects. For example, Mars is about 20 arc seconds across right now. That's pretty darn small. I mean, remember, a degree is 3,600 arc seconds. And the moon is half a degree. So when you're looking at something that's 20 arc seconds, you're looking at something that's a tiny fraction of the size of the moon. Or when you're looking at a lunar crater, you're looking at something that's a tiny fraction of the moon. In this image, for example, the smallest detail is about an arc second or so.
Wow.
So you're looking at objects that have extremely small, they're extremely small and you're trying to pull out very fine detail. And there's two problems with this. Number one, you need to have tiny little pixels to capture that detail. You need to have a long focal length, and you need to deal with this pesky thing called atmosphere. We have to breathe, so we've got this thing called an atmosphere. The problem is it's turbulent. And in the old days, if you go back and look at pictures taken with film cameras just 20, 30 years ago, you'd never see detail like you see in that picture Greg just showed, or that Mark was showing. You'd never see that detail. And that's because of atmospheric turbulence. It's not because the optics were bad back then. It's not because the film was bad. It's because they were taking individual exposures and they could only take a few dozen. So the solution is to get a camera that can take many, many short pictures and download them into your computer. And a normal DSLR can sort of do that if you put it in video mode, but it can only really typically shoot about 30 frames per second, and that's kind of marginal. The really good pictures, Greg, by the way, how long, or maybe you'll tell us, but how long were the exposures that you took for your shot?
I will cover that, and it was a video. It was like a 25-second video, and the exposure was 1/500th of a second.
Yeah, see, and the reason for that is it freezes the atmospheric turbulence. And then the software goes through and as Greg will demonstrate, the software goes through and picks out the winners from the losers in the frames. The reason you get away with, and of course you also use all small pixels to oversample, because the same software that weeds out the good from the bad images will actually do what's called dithering between those samples. And you'll actually get better resolution than in theory your telescope can produce. We used to use that for decoding radar signals back when I was doing that business. And back then, of course, we didn't have the advantage of these kind of processors. We had to jump through some real hoops to do it. The reason you can get away with short exposures is because there's lots of light coming from these targets. And as a result, noise is not an issue. However, even though there's lots of light coming from these targets, when you run them through Barlow's or eyepiece projection to produce an effective longer focal length, which means a bigger picture on the film plane, when you do that, you do reduce the amount of light. So some of the better planetary cameras are more sensitive than your normal DSLR is. So there's really three planetary options. One is a small consumer camera, a small DSLR will do, with a video recording mode, like Greg was saying. But Greg's is recording video, but it's recording at a much higher frame rate. For example, the little one I used to take those pictures I showed at the intro, those 3 pictures, that was taken with a camera that can only do 30 frames per second. So it could only really do decently under very good atmospheric conditions. However, there are some caveats on using consumer cameras for this purpose, to record the video, which then the software weeds through, as Greg will describe. They first have to have adequate manual controls. Not all consumer cameras do. You have to have one that does. The camera lens essentially replaces the eyeball behind the eyepiece in many cases, and that's called afocal or digiscoping. Because you have to replace the human eyeball with the camera, you're not going to be able to hold it manually over the camera and take this video. It has to somehow mechanically couple. An advantage of this technique is you don't need a computer to capture. Okay. The other options are a specialized color solar system camera that replaces the eyepiece. You take the eyepiece out completely and you stick the camera in the telescope, which may or may not have a Barlow. It may or may not use what's called eyepiece projection. Essentially, the camera replaces the eyepiece completely. With these, you can get higher frame rates if you buy the right one, and they'll have small pictures, and the images captured goes to the computer. In the case of using a commercial consumer camera, your memory card in it may not have enough memory. In the case of a camera, in the case of downstreaming it to a computer, you've got gigabytes. You may, however, have to have a USB 3 camera, not a USB 2 camera. So you got to watch for that. And then the final is, and I've seen some very nice pictures taken with these from other locations with much bigger telescopes. You get a monochrome USB solar system camera and use filters to take a sequence of video in red, a video in blue, a video in green, and then recombine them to get the color and the best image in each color. And that's much more elaborate. And of course, it's very difficult to do on planets like Jupiter because they rotate pretty bloody fast. It would work on Mars, and I've seen some, but that's a totally different magnitude. I've gone from ease of use to medium use to much more difficult. The best part about all this is that there's freeware to process the images, as Greg will describe. None of this is going to get done without a computer, whether you capture the data or not. Here's some examples using regular cameras, including a cell phone. We've got one of these and we let the public use it. It's a bracket that holds the cell phone over the eyepiece. The eyepiece is on the camera, it clamps to it. And the trick here, of course, is you got to be able to adjust the camera so the eyepiece output goes right into the camera. This is a little more illustrative, perhaps. Here's the regular eyepiece, and the human eye is just replaced by a camera. One of the challenges, of course, is you have to space the camera so the entrance pupil to the camera is where the eye would go. And so you may have to slide this back and forth and experiment a little. But once you do it with a given eyepiece, it won't change. Another way of coupling the camera to the telescope is some eyepieces actually have threads on them, and you can buy couplers so the camera is rigidly attached to the eyepiece. And all three of these are called afocal or digiscoping. Another option is to actually use the eyepiece as a magnifier, and then you put some spacers between, and this is showing a rather elaborate rig. Somebody's trying to sell you a lot of hardware. Imagine it's just a long tube. So if you were to screw this with a long tube and connect it to your camera without the lens on the camera, then this basically becomes a magnifier. And that's called eyepiece projection. With any of these, you can stick a Barlow between the eyepiece and the telescope to get an effective longer focal length. Or you can just run a Barlow straight, without any of this, a Barlow straight into the camera. And I think that's what both Greg and I think Dan Scosa did. And the purpose of that is to get a bigger plate scale, more pixels per arc second, so you get better resolution. Here's some examples of solar systems cameras. This is a little hockey puck shaped one that goes on a USB. Celestron makes a whole range of these things with prices ranging from $150 to 400, 500 bucks.
Yeah, the fourth one there is the one I use.
Yeah, the Skyrex 236C. Yeah, those go for about, what, 300 and something?
Yeah, I think it was 350.
Yeah. And what you're paying for here is these models, these three models here, and Celestron isn't the only one. You know, you've got to look through the market to see what suits your purposes. The difference here is that these three models have a much higher frame rate. They will go up to 200 frames per second and exposures of 1,000th of a second. And they have higher sensitivity, so you can use the shorter exposures. I have one of these, and I took some Mars pictures, and they're about as good as what Dan took. They're not as good as what Greg took because he's got a better camera and he's got the skill to use it properly. So there's a price range over these depending on how serious you are, which is another way of saying how much time you want to spend and how much money. The next Imager 5 and the next Imager 10 are basically, some people consider them entry-level cameras. These are a little bit more expensive, but they do a better job. And this is a monochrome model, by the way, so this would typically be used with the filters in front of it. And I'll talk about filters more when I come to deep sky. These are all CMOS, and they all have the filters stacked on top of the pixels, as I showed here. Okay? These are like little bumps, little domes on top of each of the pixels. The odd thing is, CMOS, in the CMOS world and in the CCD world, monochrome sensors cost more than color sensors. And I think the reason is because the production volume's lower. But there's an actual additional manufacturing step needed to put these filters on. So actually the monochrome should be cheaper. But I think it's a marketing perception and a market size. So you can even get small chip cameras that are cooled with a filter wheel. This is sort of the ultimate. I've seen some pictures taken with these. It has a very small sensor like all these do. For example, these sensors here are like 4 or 5 millimeters across compared to a standard digital single lens reflex sensor that's 18 by 24 or 16 by 24, or a full frame that's 35 by 24. So these are very small, but they don't need to be big because the planets are very small. Okay, so then the next topic is deep sky. To summarize though, with this, what's the point of all these cameras? They have to have high frame rates so they can get this, so they can shoot through good spots in the atmospheric turbulence. So you want high frame rates and you want to have small pixels. And they don't have to be as sensitive because you get lots of light from these targets compared to a galaxy or something like that. Deep sky's a totally different game. The targets are all very faint. By the way, these are real spikes. They're not faked put on by a software. Those actually came from the spider on my 12-inch telescope a number of years ago. But these objects are faint, so you've got a different set of requirements. Typically, you need exposures in the range of tens to hundreds of seconds instead of tenths of a second or hundredths of a second. You can use a regular camera that's computer controlled, or you can even use one standalone. You can use one with or without filters in front of it. The red, blue, green filters are to get color. The other kind of filter you use is a light pollution filter, which we have to use around here even with a single shot color type of camera. So there's a regular camera. You can take a DSLR and do some good work with it, especially if it's been modified. That used to be very popular and it still has its uses. Specialized deep sky cameras are different flavors. There's the single shot color and there's the CCD that we talked about. There's a religious, it gets into a religious discussion over which is better, CCD or CMOS. All I can say is that Sony, which knows the business, has exited the CCD business because they just don't see the market for it anymore because CMOS is so good. And most of the cameras you see offered for sale now, if you go look on the various astronomy dealers, most of them are CMOS cameras now, the vast majority. CCDs are still viewed as a premium item. If you want to spend thousands of dollars to get a medium-sized chip camera, you can certainly do it, and you'll take some good pictures. But most people, like if you look at what Andy's been showing, most people can take perfectly good shots with a CMOS. So either one of those will work. Depends on your taste and how much money you want to spend, quite frankly. There are some advantages to either one. There's color, whether it's CCD or not. And there's monochrome, whether it's CCD or not. Essentially, a specialized deep sky camera that's single shot color is essentially a DSLR on steroids. It's got better electrical sensitivity in terms of noise, and it's got cooling usually. And that's what you want in most cases. The reason you want cooling is it reduces thermal noise. The reason you want a specialized deep sky camera is because they're designed specifically for long exposures and therefore address electrical noise very aggressively. Whereas your normal DSLR type camera, electrical noise is dealt with. They do their best, but they got to compromise a lot of other things because they're making a camera that has a lot of purposes. So you pay for the specialization and you get a little bit better results. The cooling makes the biggest difference because it reduces the thermal noise. The reason this is important is because at the low light levels that we're working with on these kind of subjects, the thermal noise in the camera can actually appear in the image. And you can't escape it because when you're looking at things like this, you're looking at images made up of dozens of photons, not millions, which normal light levels provide. Okay, so to sort of summarize what happens when you do long exposures. This actually tells the whole story, not just the camera side. Well, you can do it with a DSLR, and I've done this myself. So you can take a DSLR, put the optics in front of them, and the images go to your memory card in your camera. And then after the next morning, you go out and you process it. Hold on, I got to change pointers here. Okay. Or you can take your color, be a single shot astro camera. Uh-oh. Am I losing my internet? I guess not. Can people hear me?
Yeah.
Okay, because I got a warning screen that came up and said my internet's unstable. So you could have a color camera that's either a DSLR with or without the filter removed, or it could be a specialized color astro camera, which could be CCD or it could be CMOS. And then you take the data out of it and you ship it, you export it immediately to the computer and you control the camera through the computer. And then the same deal, you take the image files, instead of pulling them off your memory card, you pull them off your computer and process them after, the next morning. Or if you're really psychotic, you do it the same evening before you go to bed. Okay. Now, any of these options can use a guider, and the more you use a guider, if you use a guider, you can shoot much longer exposures. Because again, the number of photons you capture is precious. So if you can guide and take a picture for 10 minutes instead of 10 seconds, or even 2 minutes instead of 10 seconds, you'll get much more signal, which makes things better, easier to process. You won't have to dig down into the noise to dig your image out. The final option, with or without a guider, but usually with a guider, of course, is you have your monochrome camera and you take a series of exposures for luminance, red, blue, and green. So for each, instead of taking one exposure, say 10 or 12 exposures, you take 4 times as many or 3 times as many, and then you take those individual pictures and you process them to produce the color. Now, those of us who are old enough or who have their father's books on photography from the 1930s know that when they first did color photography, that's how they did color landscape photography. They actually had cameras that had black and white film in them, and they put different filters in front of the lenses. And then they combined them in the darkroom. Well, that's what this is. This version of long exposure, you're essentially doing the same thing. You're taking different exposures and recombining them to produce the color. I don't know if any of you have been out to, I think it's in Utah, the Kodachrome State Park. There's actually a state park named for it because it was when National Geographic took the first test batches of Kodachrome film from Eastman Kodak out there. So again, to summarize this, you can have a standalone camera like a DSLR with or without the filter removed and take your pictures. And you can have guiding in this option, obviously. That's always an option and recommended. Or you can take your color camera, which could be your DSLR, or it could be your specialized astro camera that has a USB interface, and send commands and download the data and store all of the data on your computer directly, and then process it later. And again, as I said, any of these options could have a guide camera. The option with a standalone color camera, if you don't have a computer, you're not going to be able to do guiding very well. But once you go down this route, you've got a computer, and so it's easy to do the guiding. And then finally, with a monochrome sensor, you actually take different sets of exposures with all the filters. Okay, so how to choose which you should do for any one of these applications, whether it's solar system or deep sky. Well, there's the size of the sensor, which determines the field of view. If you want to be able to take good lunar pictures, you need a bigger sensor or a shorter focal length than if you want to take pictures of Mars, because Mars is 22 arc seconds. You need a long focal length and small pixels. When you're dealing with deep sky stuff, the physical dimension of the pixels actually becomes important as well. Because with smaller pixels, there's higher counting noise at low levels. This has got nothing to do with thermal noise. It's got nothing to do with electrical noise. It's quantum mechanics. The smaller the number of photons that you capture in a pixel, the worse the signal to noise is. So that means that with deep sky stuff, you actually want, within the limitations of resolution, you actually want larger pixels. So if you go look at the dealers and look at their highest end cameras, monochrome cameras with 40 by 40 millimeter sensors that cost $20,000, they have 9 micron pixels. That's the exact opposite of what you want for solar system, where you want 2 or 3 micron pixels. So, and the reason they have big pixels on those cameras is because they want to get lots and lots of photons in each pixel, because that determines the counting noise of the camera, which is going to happen no matter what else the engineers do. The only way to get around it is to have longer exposures. Then you get more photons per pixel and the counting noise goes down, relatively speaking. Other key performance parameters, particular for deep sky, is what's called the quantum efficiency. This used to be the big advantage of CCDs. Right now it's a tie. both of them are about 80%, which means 80% of the actual light that comes into the camera gets captured and turned into signal that the camera can read. The other key performance parameter is readout noise, and that's important for both planetary and planetary solar system cameras and deep sky. You want low readout noise, which is part of why, for example, the Skyrex cameras are more expensive. They not only have a higher frame rate, they have a lower readout noise. Readout noise is electrical noise introduced into the signal. And then finally, there's thermal noise. And the only way to handle that is thermoelectric cooling, or have really good heating fins on your camera. If you look at the Skyrex camera, for example, oops, where am I going here? Sorry. I guess I went past it.
Yeah.
There we go. See these little things? Those just aren't there for decoration. Those are cooling fins. Now, they're not going to do a lot of cooling, but in the steady state, they'll actually help reduce the thermal noise in that camera. They're not just fins like on a Chevy. Okay, so it's handled by thermoelectric cooling or by cooling fins. Now, cooling fins don't work very well for deep sky cameras. They do sell deep sky cameras without thermoelectric cooling. If you have to save $100, okay, but I don't recommend it. The big reason to go to a dedicated astro camera, in my opinion, over a DSLR is this. Because you do get better pictures because of that. There's less thermal noise because they're cooled.
100% agree.
Yeah, if you look at, if you take most digital, if you turn off the most digital SLRs, off the shelf consumer cameras that, you go buy for $500 or $300, those are nice cameras. I've got 2 different types of those that I use for travel photography, for birds, and for some astrophotography. But they, if I take a long exposure and turn off in-camera noise reduction, I can actually see the thermal noise. It's commonly occurs in one corner of the sensor because that's where the amplifiers are and they generate heat. So that's why if you want the best possible deep sky camera, you should get one that's thermoelectrically cooled. Now, the ironic part about this is not exotic technology. The thermoelectric cooling uses a chip that costs $5, and you can go buy recreational vehicle beer coolers that have half a dozen of those chips in there. So it's not some exotic technology, but it's not a normal thing you would put in a camera that people use to walk around and take pictures of architectures or pictures of people on the street or whatever, or birds or whatever. That's one of the big delineations between a standard DSLR and a dedicated deep sky camera is this. Yes, they've improved. The readout noise circuitry is better. They do better noise handling in the astro cameras, but the real big difference is the thermal cooling, which takes some power in the field, by the way, but not a huge amount, a few amperes. Okay, so I think that's the main point. Again, with it, you have to look at your application to decide what kind of camera you want to use. And then you have to decide what you feel comfortable using. Once you start guiding, the difference between a DSLR and a dedicated astro camera is how much money you want to spend. I first got into guiding with film. I mean, I've been doing it that long. Then I went briefly to a DSLR with guiding, and then finally I ponied up and bought one that was thermally cooled. But I still do, by the way, personally, I still do single shot color, partly because of the climate. This is one little word of warning I wanted to give. When you read the advertising for the cameras, whether it's astro cameras or otherwise, the manufacturers are, in some cases, I would characterize less than honest, because they will say that their camera has a 1-inch format sensor. That's not 1 inch. A 1-inch sensor, in fact, is like 11 millimeters on the side, which isn't even half an inch. The reason they do that is the electrical engineers characterize the sensors by the total footprint of the sensor, which includes all the support electronics and even the pins to go into a socket. So when an engineer says a 1-inch format sensor, he doesn't mean 1 inch of sensor area. It's actually smaller. So these are some pretty common ones. For example, a 2/3 format. Well, 2/3 of an inch is what? 18 millimeters. No, a 2/3 inch format is 8.8 by 6.6 millimeters. That's nowhere, even the diagonal is nowhere near 2/3 of an inch. In fact, the diagonal would be barely 10 millimeters. 10 millimeters is not 2/3 of an inch. So you got to be very careful. I was recently looking at one of the dealer websites and they listed the specifications of the camera and they said 1-inch format sensor. And then I read further down and it said it was X pixels by Y pixels and the pixels were this big. And when you multiply them out, it's 11 millimeters by 11 millimeters. It's not 1 inch by 1 inch. It's not even half an inch. So you got to be very careful when you read the specs. Okay, so that's my little bit of a word of warning on this. You got to read the specs very carefully. So if somebody says they have like a 4/3 format, you would think that's 1 1/3 inches, right? Which would be 25 millimeters plus 8. So that would be 33 millimeters. No, it's not. It's 17 by 13. And again, the diagonal would be barely 22. So these numbers, these kind of numbers overstate the actual active area of the sensor. So you have to do a little bit more digging, not a lot. You usually just go down the column and eventually they'll tell you it. They'll tell you the diagonal or they'll tell you how many pixels by how many pixels and they'll tell you the pixel size. And then it's just it's just multiplication. Okay, so I hope that isn't too boring to people. Probably many of you knew some of this or all of it, but I'm done sharing, I guess. Unless somebody has a question I need to go back to.
Very informative.
Yeah.
Okay.
Thanks,
Saved
Mark.
me a lot of explaining. That was great.
Thanks, Mark.
Yeah, I enjoyed
My
that
pleasure.
very much, Mark.
Yeah.
That's what happens when you let an engineer share.
I
Well,
plan
that'll
on
never happen again.
starting to try imaging with my cell phone, so I was very glad to see that in your presentation that